All right, so it's 2, so I guess we should get started with doing some stuff. Alvaro wanted me to show you all how photogenic we all are, so good job on having your picture taken. So maybe I'll jump back to the magma calculator. So, Keith, do you want to keep looking? Oh.
Oh, I see. 85 smiles. You were right out. Okay.
I would like to point out, no one told me to smile. What, that?
Zoom in on me. I'm right in front of you.
Oh, yeah. No one told either of us to smile. So next time you'll have to remember that, Alvaro. Tell people to only take half sandwiches, and the photographer needs to tell us to smile. All right. So let's go to less exciting things and talk a little bit about magma again. So I wasn't planning on it, but I think it might be nice to go through the example that Eric had worked out in his lecture today of finding full 5 torsion of an elliptic curve over a finite field by extending and adding roots of those polynomials. It's a nice example of doing a couple extensions and defining a point over a number field and computing its order and Frobenius and all of that fun stuff. So if you remember, the elliptic curve we were working with was the elliptic curve y squared equals x cubed plus x. So we can give that in short form as 1, 0. So let's just double check, submit. And there we go. We've got the curve that we want. Wonderful. And we wanted to think about it, though, over GF11. So let's let EP be the elliptic curve. Oh, I'm lying. Let's do base change with an S, e to the finite field with 11 elements in it. And I guess I'll just do EP to double check that it's happy. The change should be capitalized. Camel case, right? Well, I want to do something later with the elliptic curve, reducing it mod lots of primes and computing the trace of Frobenius for all those primes. So it's easier to start with it there. But I think I want change ring, in fact. This is one of the frustrating things about magma is you do base change when you want to extend the base, and you do change ring when you want to coerce it somewhere else. So there we go. Change ring. Okay, now we're happy. And I think we saw today that this had 12 points, so let's just double check that that's actually true. The number of points we have, yes, correct, is 12. And so we did this by computing the trace of Frobenius for P equals 5 and 11. Right? And so what we wanted to do in order to do it for 5 is find the field of definition of the full 5 torsion and compute a matrix representation and compute the trace of that. So let's do that. Let's start by defining our division polynomials. Let's do division polynomial for EP, and I want to do the 5 division polynomial, and let's give this a name. Let's be real creative and call it F. Oops. There we go. And let's grab its factorization. Let's call our factorization. Yep. Factorization of F, and let's just look at what the factorization is. Submit, and there we go. Eric was not lying to us. It actually is x squared plus x plus 6 times a bunch of other quadratic factors. And so we'll just pull off the first quadratic there and look at the extension of GF11 by adjoining a root of this polynomial. So we'll let F1, and maybe I'll stop returning that. We'll let F1 be the first term in the factorization. And remember, the factorization gives you an ordered pair. It gives you the polynomial and the power. So you have to take the first entry of the first entry in order to get that polynomial. And just to double check that I'm not lying to you, submit again. There we go. We've got our polynomial. And now we'd like to look at GF11, but extended by this F1. So we're going to adjoin a root of this, and maybe I'll give it a name. KA is what I think Eric called it. And K is submit. finite field of size 11 squared, right? Of course, I could just base extend this to GF11 squared, but then I don't know what my generator is, and I want this particular generator because this particular generator will be the x-coordinate of a point of order 5. And so now you want to know, well, is square, if I plug this in to for the x-coordinate, I would get y squared equals a cubed plus a, and I want to know, is that a square already? Should I expect to actually get a point of order 5, or do I need to adjoin a square root again? Oops, yep, I got it. Square, submit, false, not going to be a square. So that's a bummer, but not so bad. What I'll do now is I'll define a polynomial ring y whose coefficients are going to come from my field K, and I'll do an extension now. Let's call it L. I'll do the extension of K by the polynomial y squared minus a cubed minus a, right? I want a cubed plus a to be a square root, or to be a square, not a square root. And let's cross our fingers that this worked. Submit, what did I do? Oh, I don't want a comma there, I'm sorry. It's a vertical pipe. Now we're up to our finite field of size 11 to the 4th. Let's now do our base change. So let's let EP4 to the 4th power be the base change this time of EP to L. Double check that that's actually correct. Seems to work. And now I can define a point P by, it's on EP4, and it'll have coordinates A comma B. And we can ask, well, what's the order of this point? And fingers crossed. Hey, look at that. We really did get a point of order 5. So now we have a point of order 5. You may want to go back. I guess we saw before that there were only 12 points defined over GF11, so it can't have a point of order 5. But you may want to know what actually was the group, the abelian group. EP. Submit. And oh yeah, it is cyclic of order 12. Right, so I didn't have full 2 torsion and a point of order 3. I had a point of order 4 and a point of order 3. Wonderful. Let's get rid of that. And let's come back down here. And now what we needed was, well, let's actually double check that we actually get both points of order 5 here by just asking what is the abelian group EP4. We really have full 5 torsion. And oh yeah, look at that. Z120 cross Z120. So that's good. We really have full 12 or 24 torsion and our full 5 torsion as well. And so, but now we want to get our hands on what that other generator is going to be for our 5 torsion. What's our other independent point of order 5? And Eric suggested that we just let Frobenius act on this. And we define Q to be the point on EP4, whose coefficients now aren't A and B, but A to the 11th and B to the 11th. Let's see what the order of Q is. Well, let's just see what Q is. Submit. Oh, and you know what? Just for the sake of simplicity, I don't need this anymore. Submit. So there's my point of order 5, exactly what Eric told us it was. And we're in good shape. Everybody all right? And now the question is this genuinely an independent point? Are P and Q independent? Or is P or Q a multiple of P? So you could check maybe for n in 0 to 4, do n times P, capital P equals Q. And let's just see that these are n for always false. You do something more sophisticated so you don't have to look through a list of falses, but there are only 5 of them. So we can really see these are never equal. And so these really are independent points. And so this does form a basis for our 5 torsion. Everybody okay? Making sense? And so then the next question is, well, what is Frobenius' action on Q? We know what it does to P already. It takes P and sends it to Q. What does it do to Q? Well, let's again take our points. Excuse me. Let's take, sorry, that's what I want. Let's take Q. Oh, well, let's get rid of the N4 for now. Let's look at the point that's given by, it'll be EP, on EP4, where I'll take the first coordinate of Q and raise it to the 11th power, the second coordinate of Q and raise it to the 11th power. Maybe I'll give this a name, we'll call it R. Let's see what R is, submit. And it's A, 10, B, and 1. And from this, you can really read off this is going to be minus P, right? The P and R have the same X coordinate. Their Y coordinates are different by a minus sign, but maybe you don't trust me. Maybe you think weird things happen over finite fields. Minus P equals R. Submit. That's true. And so Frobenius takes P to Q and Q to minus P. So when you make the matrix representation, whether you decide to do that with rows or columns, you'll get that the trace is 0, which is wonderful. Fantastic. So you could have computed this directly without going through all of the human code of doing this, typing and whatnot. You could have just asked for the Frobenius. I'll double check I remember exactly how to do this actually. Trace of Frobenius. Can't type today. R-O-B-E-N-I-S. Frobenius. Did I get that right? So E11. What's that? Frobenius. What am I doing here? Yep. And the trace of Frobenius is 0. And so you can actually also do traces of Frobenius. Notice here I'm giving it the original elliptic curve over Q and a prime. If I do traces of Frobenius, it'll give me the traces up to 11. So I have the trace of 2, A2, A3, A5, A7, and A11. So you can do this for lots of primes reasonably quickly. If you want to see how long a computation takes, you can, of course, look at the bottom of the screen, but that'll tell you how long everything you did took. If you want to know how long it took to do a single one line, you can just put time in front of it, and it'll return time just below. And, well, it took 0 time. I find that hard to believe, but I think that this is just because I've already loaded it once. And in fact, the next thing that I wanted to do just while we're here, there's been some talking about efficiencies and how hard it is to do various computations. It might be nice to see, is Magma any good at counting points on elliptic curves over finite fields? And so let's just keep our elliptic curve the same. Maybe I'll come up here. Let's just delete all of this, I think. Yeah, whatever. Let's just do it. EP, I want to just go to a random prime P. So let's let P just be a random prime. Let's start with less than 2 to the 10th. Let's return our prime. Change ring. Let's do time and the size of P. It's probably not. Submit. Did I lose a colon somewhere? Oh, not size of P, EP. Excuse me. Not so surprising that that wasn't too hard. What was I going to do? I was going to do a bunch of these. Random prime. Oh, yeah. So let's see what happens. I mean, it should get harder and harder as my field gets bigger, but rather than letting my field get bigger and bigger, let's look at GF, larger powers of our prime P. So let's do 4K in, let's go, I don't know, 1 to 10. Do the number of points over GFP to the 10th, or excuse me, GFP to the K power. And 4, and see how long each one of these computations takes. These are all taking 0 seconds despite having lots and lots and lots of points. Oh, I lied. One did take 0.1. There we go. And my guess is this is just like the fractions all adding up as we go, right? And this is sort of the power, right? Like I was talking about, if you do this for a prime, then going up is actually pretty easy. And so, okay, maybe this isn't so impressive because my prime is 647. It's not the biggest prime you can imagine. We've seen lots of things about large primes and why large primes might be important. Let's see if we bump this up to 50 bits, if we get anything more substantially complicated. There's our prime now. It's a big prime, maybe not huge, but big enough. We're not breaking any records today. But you can see that the computations are still pretty fast, all things considered, less than a second to do that prime to the 10th and compute the number of points on there. It's worth pointing out, though, if you change this from compute the number of points to actually compute the points on the curve, it's a different story. Right? It's much, 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 much harder to get your hands on the points themselves. So don't ask it to compute all the points and ask for the size of that list. Not that anyone would ever do that or would have tried to have done that earlier this morning and realized this is a bad way to do this. It is worth, though, pointing out that computing the number of points on an elliptic curve over a finite field is very efficient because of all this stuff that we've been learning about. Now, does anyone who's maybe more familiar with elliptic curves recognize this elliptic curve, y squared equals x cubed plus x? It's a fairly special elliptic curve. It's J invariant. I should probably just, oh no, we're good. This is a problem with going from a Mac to a PC. I don't know where any of the hotkeys are anymore. Let's just batch comment this out for a second. The J invariant of this elliptic curve is 1728. And if you've heard about taxi cabs before, you know this number 1728, right? It's 12 cubed. This is, what?
Yeah, it's the smallest number is the sum of two cubes.
1728 is one of the cubes, right?
Yeah.
It's plus 1. But this is how I know that 1728 is a cube, because it's plus 1 is 1728. Yeah. It does make an appearance. It's maybe not the number of the taxi cab. But in any event, this is a really special elliptic curve. J equals 0 and J equals 1728 are ones that pop up as exceptions all the time. They have a larger endomorphism ring than expected. And so you might think to yourself, well, self, this is probably just an artifact. Am I the only one who calls himself self? This point counting might be an artifact of this being a really special curve. And so maybe you want to work this one more time with not this special elliptic curve, but instead a random elliptic curve. So let's just grab a random elliptic curve from the Cremona database that we saw yesterday. So we'll let DB Cremona database. And now, whoops, don't forget your semicolon. Now we'll have E just be a random E. Oops, nope, and a random D. And let's just see what curve we have. And just for the sake of making things interesting, what happens if we really bump up the prime? Submit. I mean, I should try and go 2 for 2, breaking magma. So here's our elliptic curve. Y squared equals much messier. And I guess it would help to do this. Again, the point counting is still somewhat surprisingly good. I mean, actually, it almost seems like it's better now. Right, and how big was our prime? Let's see. I didn't even point that out. Yeah, there's our prime that we're looking at. So this is pretty impressive, I think. You can count points pretty easily, and it will compute points and give you lists of these, the points over these finite fields, but it'll take much longer to actually get your hands on those. So really, the motivation for doing this extra example is to show you how to just grab a random elliptic curve E from your Cremona database. Now, maybe I should just point out one thing. If I hit submit again, it takes a little less time, but I get back the same curve and the same prime. When you're using the Magma calculator, when you open up the calculator, you get a seed for the randomness, right? Because it really is random. Again, you shouldn't do this when you teach with air quotes. But the seed that you have doesn't change every time you refresh it, and that's the seed that's seeding the randomness. It's probably pulling it from, like, the wind direction at the top of Mount Washington or something like that.
Washington is not very impressive.
Which one?
Pittsburgh.
The one in Pittsburgh is not very impressive, which makes those bumper stickers hilarious if you moved from Pittsburgh to here like I did. It's very small. Have we seen these bumper stickers in the area? No? This car climbed Mount Washington. Yeah, they're funny in Pittsburgh. All right. That's an inside joke for me only. I guess Keith's on the inside too now. But he set me up for it.
It's a joke.
Yes. It's a very inside joke. Yeah, so that was about as much of that as I wanted to talk about for point counting, and maybe we'll just point out one last thing with these Cremona databases before I move on to the databases of number fields. There's actually two ways to call this database, or to call different databases, I should say. Let's let D1 be the Cremona database, and D2, there's also this elliptic curve database. And you might wonder, what's the difference? Well, let's see some artifacts that I didn't tell you about these databases. So let's compute the conductor range. So I said that these databases, they're organized, the elliptic curves are organized by their conductor. Copy, paste, return, paste, D2. And so this will tell me how big and small the conductors are, and then they go from 1 to almost 400,000. I had to count the number of nines there. These are really the same database, just called them differently. You can also ask for how many curves there are, so you can do number of curves. In D1, let's just do D1, since I'm telling you they're the same. Curves, I heard us there, thank you. Hopefully you're not hissing at me. So almost 2.5 million curves. So there's a lot of curves there. You can ask how many curves there are of a given conductor. I think we saw last time that there were 3 curves of conductor 11. Nice. And if you remember, I wrote a for loop that ran over various conductors and did some computations that I think broke Magma, or the calculator went over 120 seconds. And the reason I started at 11 is if you give me a number less than 11, I don't know, 7, submit, there aren't any elliptic curves. So the smallest conductor of an elliptic curve is in fact 11. It's not totally unrelated to like no points of order 11 kind of stuff happening here. 11's a real, it's a real prime. It's not 2 or 3. Was there anything else I wanted to do? I think being able to grab a random elliptic curve is really nice if you're just trying to test some conjectures and things. So knowing how to do that is useful. Any questions? Everybody okay? You can do other things, and there's lots of information about this in the Magma handbook. You can grab the number of elliptic curves in a given isogeny class. So maybe you want to do 101A, that isogeny class. I might have to put quotes around that. I think I do. Let's grab quotes. So how many elliptic curves are there in the isogeny class 101A? There's only one of them. Neat. So you can really get a lot of sort of numerical information out of this database pretty quickly. So enough elliptic curves for now, never enough forever. Let's go to number fields and let's look at the database of number fields that's available to you in Magma. So let's start by just doing question mark number field database. So number field database, so this number field database, this command is an intrinsic. It takes as its input an integer and returns a database object for the number fields of degree d. So you give it a d, say maybe 2, and it'll return all the quadratic number fields that it has in the database. You can extend the native database by going online and downloading expanded databases. This one goes up to, it doesn't say, but it does only go up to degree 9. And I say only maybe sarcastically because we'll see there's a lot of fields here. So let's do D will be our number field database of all of the quadratic fields that are in there. And we can ask, well, what's the discriminant range of discriminant range? Submit. So the discriminants run, let's see, it's about minus 100,000 to 100,000. So pretty big range of discriminants. You might want to know, I think, number of fields in D. So how many number fields are we actually looking at here? About 600,000 quadratic number fields. And so you can start pulling these things off by various attributes. So for example, I could, let's look at a sub database where we'll grab all the elements in D. I don't want to restrict the discriminant, but let's just grab the class number. And let's get the ones that are class number 4. So D sub, hit submit. And so these are all the discriminant, all the quadratic number fields with class number 4 in here. And so you might wonder, well, how many? I wonder if this will just tell me how many there are. Yep, about 52,000 of them have class number 4. It's pretty nice. Maybe we want to try, 4 is impressive, but it's not the most impressive. Maybe we want to try 10. Do we get a bunch of those? About 4,000, excuse me. Maybe we can get class number 100. 1704 of those. Class number 1,000. Whoa, 70. So there's a lot of stuff and a lot of fun that you can have with these. And so let's just go back to the class number 4 ones. Class number 4. And let's pull off of those. If I have class number 4, that means my class group has size 4. It's an abelian group. So there's only 2 different groups it could be. It's either Z mod 4Z or Z2 cross Z mod 2Z squared. So let's separate those out and see how many of each there are. So let's let D cyclic be the subgroup of D sub, or the subclass, I should say. Oh, and maybe before we do that, actually, I just want to point out there's this weird vertical pipe and then a colon. Why would you have that be a command? Well, you can actually put information there. You can restrict the discriminant. Right, so maybe I want the smallest discriminant to be 0 and the largest to be 1,000. And I should have it return something so you don't just see this saying, yeah, that's fine. D sub now is, you can't have discriminant 0, right? Now we have class number 4 still, but the discriminant is between 1 and 1,000. So I've restricted myself to say positive 1. So that in between the vertical pipe and the colon goes a range of discriminants that you would want to work with. And if we get rid of that now, into D6. This will be the subset of D sub. Now I want the class group to be, I want this to be cyclic. So as an abelian group, its signature should just be 4. Right? It's Z4. Where the non-cyclic ones, let's make sure, let's just hit submit once. Okay, good, no error. If I wanted the non-cyclic ones, they would be isomorphic to Z2 cross Z2. And so I'll do nzic, and here I'll put a 2, and submit. Okay, great. Maybe we want to actually say something about these. Let's see what the size of D6 is, and the size of dnzic. Submit. And so I guess it might be nice to have it stop returning the number of fields in the discriminant range to make this a little more readable. So of those fields, of those about, I think we said there was what, 51,000, 52,000, about 17,000 and a half of them are cyclic, and 35,000 are non-cyclic. So about a third of them have cyclic groups, and a third of them, and 2/3 of them are non-cyclic. It's not so surprising because, well, degree 2 number fields sort of want to pick up 2 torsion. I think Farshid was talking about how we can make these things arbitrarily large by just taking the square root of a large number of primes and using genus theory to talk about what that does to their class group. Everybody okay? Making some sense? You could change this 2 to a 3. Submit, see what happens here. Now it's getting a little more biased, right? We really want to have Z2 cross Z2 less than we want to have Z4. It's not a huge number of fields that we're looking at, but maybe we'll just push it, see what happens, Z9. It's possible that eventually we will. That's a new one. It's probably, well, I don't know what it is. Let's not speculate. Let's dumb it down to 7. Yeah, now none. We don't have any in our database for degree 7 fields. But maybe you want to go to degree 3. You want to change this to class number 9. Change this to 9 in Z3, and see if we get any sort of more obvious biases. And it's still pretty biased towards not wanting to be cyclic. It looks like it's harder to pick up a cyclic group of order 9, which may or may not make sense. Now, of course, the things that Alvaro are going to talk about statistically with these are not about the group itself being of these forms, but the p primary component. So keep that in mind when Alvaro talks next about this stuff. Yep. Okay. And, well, while we're here, I should show you one more way that you can sort these groups. Instead of by class number, you can do, you can have them sort by signature. So maybe I'll call the first one 1, 1, and the second one 3, 0. And instead of putting class group here, I'll have signature. And I wanted this to be 1, 1, and signature 3, 0. So, and I don't have that anymore, so let's see how many 3 zeros we have and how many 1, 1s. So do we remember what the signature is? It's about real embeddings, the R1 and the R2. Really, the easiest way to think about it is you have some polynomial that defines this cubic extension. How many, I don't have D sub anymore, I just want D, sorry. How many of the roots are positive, real is the first number, and then how many complex conjugate pairs you have are the second number. So the first number plus 2 times the second number should add up to 3. And an error occurred. Did I not hit submit again? There we go. And so it looks like surprisingly, a lot of these want to be totally real fields. Now let's see what the discriminant range is of this number, of this set. And oh yeah, look at that. The discriminant range is biased really far on the one side to being positive discriminants. And so you can imagine a negative discriminant, maybe the square root of the discriminant has to be in there, and that would prevent it from being totally real. And so maybe if we square off the entries in terms of the discriminant, let's go, I don't know, minus 10 to the fifth and 10 to the fifth in both cases. Copy and paste. Now it's sort of biased in the other direction. Maybe this is attributing to the bias that we had before. So if you get something that's unexpected, well, hopefully you notice something that should be unexpected is unexpected. But it's worth just keeping track of like the discriminant ranges of these things. I'm not sure why they set it up to be this far biased in the positive discriminant direction. But that should have an effect on the sort of statistics that you're getting out. So it might be worthwhile if you're going to use this to, sorry, the microphone's over here. It might be worthwhile if you're going to use these databases to just keep an eye on the discriminant ranges that are actually there. They're not necessarily symmetric about 0. Okay, so with the last 14 minutes, I want to leave Magma and enter not the Sage world, sorry, but instead talk a little bit about the Lmf Db database, which is really, really, really awesome, and I want to give a super plug for it. It's worth becoming familiar with. Lmf Db it's got to be org, right? Yeah, there we go. Can't be .com. So here's our Lmf Db database, and so it stands for L function modular form database. It's also got elliptic curves and number fields floating around as well. So there's a lot of stuff happening in the middle, including some open code and some information about what's going on. And maybe I'll just start clicking about. We haven't said anything about L functions, and the first letter is L, so it's L functions. Let's look at what happens when we go here to L functions and click on the degree 1 L functions. We get an explanation of what's going on. So L functions of degree 1 are associated to Dirichlet characters. They're Dirichlet L functions. They have a functional equation. The Q is the conductor of the character. The sign, blah, blah, blah. It gives you lots of information. And then there's this beautiful graph down. Well, okay, I think it's a beautiful graph down here where it's plotting the conductor on the y-axis and the order of the character on the x-axis, and for everywhere you see a point, there is a point, and then there's two different colors, blue and yellow, which indicate if, I hope I'm remembering this correctly, indicate if the character is odd or even. And so you can go to any one of these dots. Maybe let's pick, that's a dot. And here is the Dirichlet character. Oh, excuse me. I think I can. So we have L chi S, where chi is this Dirichlet character. There's a labeling system. I think this has conductor 11 and so on. It gives you the first few terms in the Dirichlet series, tells you what the functional equation is, and then there's this whole list of invariants which may or may not make sense to you. And what's nice about the Lmf Db is that they do a really good job of not expecting you to know everything that you need to know in order when you open it, in order to use it. You can come over here to the character and click on the word character, and it'll pull up a little definition, a little blurb of exactly what it means when it's talking about a character, or what the conductor is, and how we're going to define the conductor or level of a character. And then one thing that I really wanted to point out is the imaginary part of the first few zeros on the critical line. So these are the first few interesting zeros of this L function. They're given there. If I remember correctly, these are good out to 30 decimal places. In general, after that, they're not to be trusted. Some of them might be right, but it depends. So you can get a lot of good numerical evidence out of the Lmf Db, and then there's also a graph of the completed L function along the critical line. You can see where the zeros are and what it looks like. I'm not sure if that's useful at all, but it's nice to show. I have a computer, so I should give you some nice pictures, at least at some point. So there's lots of L function information there where you can go in and you can search the database by giving it a character, by telling it I only want to look at ones of conductor 11, and it'll pull them all up for you. Maybe you know some other information. You can search for the L function that you want that way. So L functions, then there are also modular forms. Again, these are sorted by conductor. There are classical modular forms, Moss forms, Hilbert forms, all sorts of forms. Yeah, Alvaro.
Can you see how many zeros are listed for the Riemann zeta function?
Oh, yeah. Zeta zeros.
That's the Riemann zeta function?
I think so.
Yes.
Yes.
Yes, it is. How
So-
many do you want to list?
There's 100. I think we can ask for more, can't we?
List them all.
Can I type all?
Oh. Zoom down to the right margin. Drag it down. Drag it down.
I don't think you should try to scroll this.
That's what you want?
Drag down to
Use the scroll button.
Yeah, it's underneath a...
Oh.
There we go. Nope, it's underneath...
whatever. Okay.
Zoom out.
A bunch of backdoor or backseat drivers.
Try to bring the sound back on again.
What's the end page down? There we go.
Forget it.
No. Well, we're almost out of time anyhow. So there's a lot of zeros though, Alvaro, for however many you would like. And I think this is all downloadable and you could load it into Magma, no problem. Yeah, so there's the first 10,000 zeros. And that was pretty good. That didn't take very long. So I would imagine you can get even more than that pretty easily.
It gives 100,000.
It gives 100,000? Yeah. It's pretty impressive. So there's also elliptic curves. So you can go and you can search through elliptic curves. Maybe you want an elliptic curve with a point of order 3. So you want the torsion subgroup to be C3. You want maybe SHA to be 4, and maybe you want it to have rank 1. Okay. Sorry. Hit search. I can see it quite fine, so. This will take a second, hopefully not too long. This is, do you remember I had an example of an elliptic curve with non-trivial SHA? When I did the Mordauvet SHA? Nobody remembers that. This is how I got it. So it should pop out. But you can search by lots of different things. Maybe you want an elliptic curve whose Galois representation at a given prime isn't surjective, that kind of thing.
What's the SHA?
SHA is this obstruction to the local global principle that prevents us from computing it's sort of the difference between the Selmer rank and the actual rank. And here are a bunch of elliptic curves with that given torsion group. They're organized by conductor again. And just one thing to point out, the Lmf Db has adopted their own labeling system. So you have the Lmf Db label and the Cremona label next to each other, and they're really close to the same, except they're different. Which is a stupid thing to say until you've gotten them confused enough times that you realize this is a real problem. Supposedly the Lmf Db labels are created in a way that if there were, like every computer were destroyed, you could reconstruct the database in the right order. There's sort of a canonical labeling of isogeny classes based on their modular forms associated to them. So just be careful that the Lmf Db label, I guess the first example doesn't work, but the second example you can see 680, maybe you can't see. Now you can. The second example, the Lmf Db label is 68802C2, where the chromonal label is 68802B2. So those letters sometimes are different, and even the numbers are different. But if you click on one of these elliptic curves, click on the Lmf Db label. I did click it. There we go. I'm going to zoom out a little. Nope, that's in. There we go. It gives you lots of information about the elliptic curve. It tells you what the Mordell-Weil structure is. Of course, we picked this so that it would be Z cross Z mod 3Z. It tells you a generator of the torsion, a generator of the infinite part, the canonical height of its generator. It will tell you all the integral points. It notes it only lists the plus y component. It doesn't do both, plus or minus. It'll tell you the conductor, the discriminant, the J invariant, whether or not it has complex multiplication, and a bunch of stuff, including the associated modular form. It'll show you the isogeny group, the isogeny class, excuse me. So here are all the elliptic curves that are isogynous to this one. There's one other elliptic curve that it's isogynous to. So we have an isogeny graph here where there's two curves and a map of degree 3 between them. There's lots and lots and lots of information that you can get from here. And I'll just point out, if you look, which I don't think I'll be able to zoom in on, the link to this page is lmfdb.org/elliptic curve/q/conductor/ whatever the B, right? So B1 and B2, this is the isogeny class. If you go back, you just add a /2, and that'll take you to the second curve in that isogeny class. If you wanted to do this not by Lmf Db label, but by chromonal label, you just drop the, let's see, this was chromonal label, B2, right? These were the same. If you drop the slashes and just give it the /q/chromonal label, it'll take you to the chromonal labeled curve. Same thing. So that's actually how I use this the most, is by having the chromonal label of a curve I want information about. Magma spits it out. I copy and paste it into the end of the link here, and it takes me right to that page. It's got tons and tons of information. So there's more stuff that we can talk about. I guess one other thing, because I'm a fan of randomness, I guess, you can also have it spit out a random elliptic curve from the database. And so you just click random, and it'll pull up a random curve for you. So if you want to do some hypothesis testing, and you don't want to feel like you've biased yourself by picking a curve with CM or something like that, you can grab, you can grab a random curve from LMFDB. There's also a number, so you can do elliptic curves over number fields. There's genus 2 curves. There's families of higher genus and abelian varieties in general over FQ. This is constantly growing. But I was going to say, there are number fields. If you go to global number fields, there's a whole database of number fields. And so maybe you want a degree 3 extension of Q that is totally real, that is only ramified at 3. Click search, and look, there's exactly one of these. It tells you the generating polynomial, and it tells you its class group, the Galois group, everything that you would want to know about it. You can click on it and get all sorts of information for Frobenius cycle types and lots of fun stuff. So one other thing to point out, if I go back here, let's maybe do a more general search. Let's just see degree 3 extensions only ramified at 3. We should get, we get 2 of them. Great. But you can download all of this in various formats so that it can be loaded into Sage, Magma, Mathematica quite easily. I won't do it because I'm not on my personal. Well, let's do it. Who cares? Fields.m pops out. We don't have anything. Let's see. Let's cancel this. Forget it. So they download as .m files because you can just load it into Magma by typing load and then putting in quotes. Again, I'm doing this. The directory where that file is, and it'll load all of it automatically. And it loads with all the information, the class group and all that, so you don't have to recompute it again. So you can call stuff that way. So if you're unsatisfied with what Magma has already built in, you can come here and get more curves. I think that the database is bigger than what comes natively in Magma. So with the last 1 minute, I'll ask, are there any questions? Alvaro?
The curve that you had with Shah for the floor.
Yeah.
How many can go
I can get it. It said there is it said analytic SHA-4, and then it said exact next to it. I wanted to click on exact.
Oh, you wanted to click on exact? Okay. Let's see. It was rank 1, SHA-4, and torsion structure C3. My guess is in the 2 descent, it's going to use like the Vey pairing to prove that it actually is that. This search took a second, so let's just wait. Right, because it wants to give me, I should say, maximum curves to display 1. And then it would just give me the first one it found. All right, so where was SHA? Exact. If I click on exact, all right, so the analytic SHA is known. Oh, so because I have an elliptic curve of rank 0 or 1, the analytic SHA is known to be exact. Right, this is because BSD is known for rank 0 and rank 1. I started to say that, and, well, I'm on tape, so that should make me nervous enough. But that's, yeah, so that's why it's exact. I'm sure there are unexact ones. Any other questions? No? Great. All right. Thank you.